Now you've learned how to make a horizontal or a vertical dilation, or even to make a horizontal and a vertical dilation of different amounts at the same time. Now if you have horizontal and vertical dilations and they have the exact same factor, then the order that you do them in doesn't matter, and you'll basically have made a similar shape. Now I've written similar here in the mathematical sense of the word. It will be an enlargement or a reduction of the actual original. Now how do you tell which? Well, if the factor is greater than 1, then you're making the thing bigger. That makes sense, because it's bigger, it's like you're multiplying. If the factor's 2, you're making everything twice as big. Whereas if the factor is between 0 and 1, then you're going to be actually compressing it or making it smaller. And that makes sense. A factor of half would make everything half as wide and half as tall. So the take-home points of how to do this, you've already seen it really. You replace x with x over a, if a is your scale factor, and you replace y with y over a. Or if it's a function, then you can use that other form. You can take your y equals f of x. And we saw that if we were actually replacing the y with y over a, and we had y equals f of x, well, we don't often write it like that, do we? And that's why we saw that it would make more sense to multiply both sides by a, and that gives you the a over here in front of the f of x. But if you've also changed the x to x over a, that's what gives you this here. Y equals a multiplied by the function of x over a. Now you can use it either way. You can memorise this as something to do. I tend to think that this one's easy to remember, replacing both the x and the y, and then you can fiddle with the function and see how it affects it. Now we'll look at an example that's an enlargement and another one that's a reduction. So in our first example, we're going to enlarge this circle. X plus 1 all squared plus y minus 1 all squared equals 1. We're going to enlarge it by a factor of 3. That means we need to change the x to x over 3. We need to change the y to y over 3. Now we need to write down the equation for the new circle, and then we need to sketch them both. So let's start by just sketching what we have here so we know what we're doing. We've got a circle here. It's in the form x minus h all squared plus y minus k all squared equals r squared. So I can use that form to just read off the equation here and see that the centre is at minus 1, because this is x minus 1, minus 1 and 1. So if I go to x equals minus 1, y equals 1, I've got the centre here. And it has a radius of 1, because r squared is equal to 1. So that means it's going to just touch the x-axis there and just touch the y-axis there at negative 1 and 1. And it's going to go over here, and I can just draw it in there like that with its radius of 1. So I've got an idea what I'm working with. Now, enlarging by a factor of 3, write down the equation for the new circle. Well, we're going to replace x with x over 3. And we're going to replace y with y over 3. So that's quite easy to do, isn't it? And there I've got the equation for the new circle. Done. So all I really need to do here is to sketch it. Now it's not quite in this form though, is it? So it'd be handy to be able to adjust this so that I could see where's the centre and how big is the radius of this. Now this is a slightly tricky part, but I can fiddle around with my algebra here. The easiest way to get rid of a denominator is to multiply everything by that denominator. So if I multiply by 3, I'm sort of thinking that might help. But I've got a problem. This is not really 3. It's 3 that's been squared, and the other problem that I have is that this fraction is not contained in the entire brackets. I've got a fraction plus something else. So first thing I'm thinking of doing is making this whole thing over 3. Now 1 is just 3 divided by 3, isn't it? So really I've got x thirds plus 3 thirds. So I've got x plus 3 thirds. That same thing I can do over here is get that 3 on the denominator all by itself, and I've got y minus 3 thirds, which is the same thing as y over 3 minus 1. And over here I'm just going to keep it as a 1. So I haven't actually multiplied anything by anything yet, I've just changed the form of it a little bit so that my fractions are simpler. Now think what's going to happen when I square x plus 3 over 3. That means I'm taking that whole thing and multiplying it by itself. Well, the denominator is going to be 3 times 3, which is 9, isn't it? And this one's going to do exactly the same. So the way to get rid of that 9 is to multiply everything by 9. If I do 9 lots of this plus 9 lots of that, what I'm going to get is 9 ones, which is 9. Now, this is going to let me cancel this 9 with the 3 squared. That'll be gone. And this 9 with the 3 squared. So that all I'll have now is x plus 3 squared plus y minus 3 squared equals 9. And I can now read off the chart there, off the equation, and say I can see that the centre of this circle is going to be minus 3, 3, and the radius is going to be 3, because that's the square root of 9. So now I can go to draw my enlargement. Let's do this one in red. The centre is minus 1, minus 2, minus 3. 1, 2, 3, it's up here. And the radius is 3, which means it's just touching here and here, and it's extending up to level with the 6 there, and level with the minus 6 over here. And it's going to look something like this. Obviously, it's not a great drawing, but this is maths, not art. Just needs to have its important points. And then I could label my centre there, minus 3, 3, and I've got my radius of 3. Now, you need to also remember that there's multiple ways to do the same thing. So if you got bogged down with that algebra there, not to worry, there's other ways that you can do this. You could let x equal 0, let y equal 0, to show that we're going to have an intercept right here and right here. Straight away, if you know you're drawing a circle and it goes through those 2 points, you've got yourself somewhere. The other thing you could do is think, well, if I'm stretching by a factor of 3, then instead of having a radius of 1, it's going to have a radius that's 3 times that, isn't it? So it's going to have a radius of 3. Now, if you already know that, then that gives you a little clue that what you're going to need over here to get it into this form. If you know that your radius is 3, you're going to need to have 9 here. And that gives you the nice clue to multiply this side by 9 and to perhaps go ahead and multiply the other 2 sides by 9. Now let's perform a reduction. Now, this is like an enlargement in that it's a dilation in both directions at the same time with the same factor, but the factor is a fraction, something in between 0 and 1, which shows you that it's actually compressing the shape or reducing it, making it smaller. So let's start with a sketch of our original function here, y equals 2 to the power of x, which we know looks something like this. It goes through 1, has an asymptote on the x-axis, and we can label another point just to give it some vertical scale. I know that when x equals 1, y equals 2. Alright, now we need to replace both parts of it here. So if you're using the replacement method, let's go in red for the new graph. We're going to replace y with y over half. And we're going to replace x with x over a half. Now when you divide something by half, it's exactly the same as multiplying by 2. Okay, so thinking that through is going to help you a lot. So instead of dividing by a half in both cases, what I could actually do now is say that's the same as 2y is equal to 2 to the power of 2x. Now, it might be nice to then say, well, let's get y by itself. If we divide both sides by 2, then we've really got half multiplied by 2 to the power of 2x. Okay, now there's multiple ways that you can draw this. Don't forget your good old friend, the table of values. You can always draw one up, showing points of interest and key points and plot them. The other thing to remember is that with an enlargement, we're making all the points further away from the x and the y-axis. With a reduction, we're getting everything closer to the x and the y-axis. So starting with a nice simple one, let's let x equal 0. What will y be? Well, if x equals 0, we've got 2 to the power of 0, which is 1. Y will equal a half. And that makes heaps of sense just performing this with logic. This point is going to get closer to the x-axis, and the factor of a half means instead of 1, it's going to be half. This point here that we already know is going to come closer. We're going to halve this distance here of 2 to make it 1, but at the same time we're also going to halve this distance here of 1. So a point that I know, like 1, 2, is actually going to become half 1. So I can label that point, I've got half and 1, and now I've got something of a scale. Now I'm still going to have all of the usual features of one of these types of exponential graphs. So I'm still going to have an asymptote along the x-axis. And already I've got 2 points here. I can go ahead and sketch my graph in. Now you'll notice that here it looks like we're sort of halving the distance between the black line and the x-axis. And as we go up here, it's going to suddenly go steep because we need to halve, oh, that's not the correct room, generally halve the distance between the black line and the y-axis as well. So this means it's going to come in here and do a really sharp corner and then go shooting up with the same basic features of your exponential curve. And we've got a point there which we've labelled. We can double check that point. I used logic to come up with it, but let's just check that that's true. When x equals half, 2 halves is 1, 2 to the power of 1 is 2, and half of 2 is 1. So sure enough, that strategy works, and just by thinking it through, you can get a lot of the main features just by using kind of logic. The algebra is sort of there as a backup, really.